Okay, we are starting off with motion in one dimension, which is also known as one-dimensional kinematics or linear motion. And I'm going to skip right into the slides on 2-1 from your textbook. So whenever we talk about motion in physics, we're really talking about the movement of an object from one position to another. So if we're looking at that, let's say on a tape measure that you would put down on the sidewalk, like in your lab, then we could pretend that's the x-axis. So we would call the initial position, the place where you start, as x1, and the place where you may end up if you were walking as the final position, or x2. And then the difference between those two we could call delta x, or the displacement, the change in x. And here we're choosing delta x to represent that. That delta is just a Greek symbol. Displacement is a vector quantity. That means it has an amount or magnitude. Whenever you hear that word magnitude, you're just going to think size or amount, as in a number. So 5 meters, or 1,000 kilometers, or 15 feet. And then the direction. So vector quantities always have an amount and a direction. So if it's your sidewalk, it could be north or east or southwest. But when we do math, it's helpful to just refer to it with a sign of positive or negative. And so when we define a direction, we're often going to give it a positive or a negative sign, and then stick with that for the rest of the word problem, for example. I included the Despicable Me clip just because it's a great reminder of the definition of what a vector is when the bad guy defines himself using that term. Okay, so on this slide, I'm just going to draw some vectors. I'm going to simplify it a little bit by just trying to reduce them to one dimension by drawing them only on Capital Drive. So let's try that. Let's see if my ink is working here. Okay, so we're going to start at Highway 41 and Capitol here, and draw a vector going west to basically where Noodles is, but not making the turn into the driveway. So if I do that, I'm starting at that intersection and I'm drawing an arrowhead west, representing where a vector that goes from my initial position to Noodles, where my final position is. Okay, so this is vector A. Okay, so this is delta x, right? And then I'm going to draw a second vector. Maybe I'll make this one blue. And it's going to go from Noodles to Chick-fil-A. So if I do that one, that means I'm getting back on Capitol and I'm going west again, okay, to where Chick-fil-A is. That's vector B. So I'm drawing that one. And then I'm going to backtrack. Let's draw a third color. So we'll make this one green. And I'm going to draw it, end up right on top, but from Chick-fil-A to Qdoba, which is right here, okay? It's kind of messy, but that's vector C. So I did those, done, done, done. Okay, then when you add vectors, okay, well, what you're really saying is, what is your overall displacement from where you started at the very beginning to where you ended up at the very end of your journey? Okay, so for your journey of A, B, and C, what is your overall displacement? Okay, so if I switch colors again, really, here's my initial position. I'm going to call it XI, I guess. And then here's my final position. Qdoba is my final position here. So if I draw a vector, I'm just going to draw it straight from my initial position to my final position, okay? And that is that's what we call the resultant displacement vector, but it's just another displacement vector that represents the sum of all of that travel, okay? And this is the overall one, the black vector. So then I could do this as A plus B plus C, okay? Or I could say it is delta X, which equals the final position minus the initial position. Okay. So then, what are all the ways that we can keep track of position over time? In your lab, you made data tables, right? And so that's a great way of doing that. Another way of doing this is to make a motion diagram, which is kind of like a breadcrumb situation, but it's a nice visual. So you could put a dot down every second that the object is moving. And so here you can see on the left-hand diagram that this object is slowing down because every dot is getting closer, or the dots get closer together as time goes by. Whereas the object on the right-hand side looks like it's speeding up because the dots get further apart. Okay, so that's one method called a motion diagram. Another way of showing that is graphing it. So we can graph motion, and we can get a lot out of that graph. It's basically taking those dots, right, and plotting the position, the number that you have on the tape measure or the number line, and making that on the x-axis or on the y-axis, which is a little weird because that was supposed to, it was an x position, right? But it's putting it on the y-axis. Okay, but we have time as our independent variable. So that makes a lot of sense though, because then you can see as a function of time, where is this object? Okay, so then when we do that, if we get the slope of the line, that's telling us how fast the thing is going. Okay, and we all know how to do slope, so that's really useful. And if you take the slope, the magnitude of the slope, along with the sign, what you get is velocity, because the sign is telling you direction. Okay, and we know that speed and direction together are called velocity. If you just have the magnitude, the number alone, you would have that in meters per second. And when you don't include the direction, we just call that speed, like a speed limit. Like when you drive down the road, it doesn't care what direction you go, unless it's a one-way road, okay, one-way street. But when you put the speed and the direction together, we call that velocity. Okay, so when we're looking at something going at a constant velocity, we will see a linear position time graph. So we will have a function for position that is linear with respect to time. Okay, so we're used to y equals mx plus b, but in physics we are going to use variables that represent the quantities they're measuring. So we're going to have an x on the left-hand side, and then time in here, okay? So then we'll have velocity as our slope, time, and then the initial position instead of our b as the y-intercept, okay? The AP sheet gives us the entire equation for the position as a function of time, including when there's acceleration. But in this unit, we're just gonna focus on constant velocity, no acceleration. So we've eliminated this first term, or this last term. So let's write the equation of this line here. We know the y-intercept here, so this is the x0 value, right? And then we need to know the slope. So vx0 is the slope of this line. So that would be like, if I'm picking this point, this would be 0, oops, it'd be nice if I would put the units. 0 seconds, it's at 8 meters. And then at 4 seconds, it's at 0 meters. So then when I do the slope formula, I'm gonna, sorry, wrong units. I'm going to do, y2 minus y1 over x2 minus x1. So I'm going to get a slope of -8 meters over 4 seconds, or -2 meters per second. So then the equation of the line will be 8 meters plus -2 meters per second times time. Okay. What physical significance do x0 and vx0 have? Well, x0 is the initial position where this thing was at time 0. Okay, and vx0 is the constant velocity it's traveling at, right? So it's traveling in the negative direction. It's traveling toward the origin, okay? That's what we know about this object. Okay, and then there's the concept of average speed, which is not necessarily the average of all of the velocities. So you have to be a little bit careful here. But the average speed is the total distance you covered over the time interval it took, okay? It's always positive. It doesn't include the direction. So while the displacement of something might be very small or even 0, right? So if you think about race cars going around a track, they spend a lot of time going in circles. Their displacement might be 0 if the start line and finish line are the same. But they've gone a lot of distance. There's a difference there, right? So then they would have a high rate of speed if they've gone a lot of total distance in a short amount of time.